And I would like to introduce our speaker, who is Dr. Nicolas Gaillard. I hope I said that correctly.
Very good
Uh,
pronunciation.
Thank you. He's graduated from CPE Lyon Chemical Engineering in 1998, and he holds a PhD in polymer chemistry from the University of Lyon, 2003. He joined SNF in 2003 to develop associative polymers for EOR, and in 2006 he became oil and gas lab coordinator. He acquired experience from many different projects worldwide: Oman, Canada, China, North Sea, Middle East, South America. And in April 2020, he joined Polytech as their technical advisor and sales manager. Uh, Dr. Nicolas has authored and co-authored of 25 publications and 7 patents. It's a pleasure to have you here today. You can go ahead. Thank you.
Yeah, thank you very much for the introduction. Hello, everybody. So today the topic is to talk about the new polymer technology for sound migration, mitigation, and geothermal energy application. I have a layout with a few words about power tech. Then we go through the sound control technology. We will see the application on oil and gas wells and how can we transfer the technology to their geothermal application with the work we did in performance test for the geothermal application. So first of all, a few words about PowerTech. It was created in 2007, and PowerTech means polymer for well technology. So we provide the polymers initially for enhanced oil recovery, but we use them for water shutoff, conformance, EWAR, and obviously sound control, which is the topic of today. We have lab capacities. We can do reservoir simulation. We can do the screening of product. We do the design of operation, and we supply the product, and we have a staff for the field assistance. We are a very small company in the west of Paris. We are only 12 people. And we have big lab capacities, and mainly our lab work is to perform core flooding to assess the transportation of fluid in porous media. So as you can see, we have performed more than 800 core flooding since 2007 and is still ongoing. And we can work with carbonates, sandstones, water. So now let's move to the interesting topic of today about the sound control technology. So as you may know, in all the wells, when you have unconsolidated sound can be a big problem for the operators. It's something that accumulates with time, so it can increase with time. It comes from rock erosion and deconsolidation. You can have degradation of the well, of the pump, of surface facilities. You can lose the productivity of your well because of sound accumulation in the well bore. You can lose the injectivity of water injectors. And very often, sound screens and gravel packs are not efficient enough because we have to deal with very fine particles that can pass those mechanical or even gravel packs filters. So what is presented here is a polymer system. I will explain the technology. And we have very good results so far in both oil and gas wells. So on this scheme, this is a representation of a pore throat in a porous media. So you have a grain of sand with a fluid that can propagate in the interstice between the grain. So here you have the rock represented by natural cement and sand grains. And here you have the fluid that can circulate. In order to better understand, we are close to a production well that is on the right on this scheme. So when you produce in the right, you have a migration because of the sun, because it's not really well consolidated and the flow rate is really high. So this is the phenomenon you have when you have sun migration. The treatment consists in injected water with a polymer that has really sticky property. It will adsorb on the surface of the rock, but with a very thin layer. It will not affect the relative permeability of the porous medium. So you have the polymer adsorbed, and when you restore the flow, you have stopped the migration of the sand. So the principle is an injection of an hydrosoluble polymer that provide a film on the surface of the rock. It's a patented technology. The injection is performed bullheading. Obviously, it will target the hypermeability zone in the reservoir around the well. There's no need of workover unit. It's environmentally friendly because and it's not hazardous. We use polymer that are used in water treatment plants, so and even for potable water. So it's very very nice. It's only one product, and there's no risk of well production impairment or injectivity impairment. Typically, the target around the well is between 3 to 5 meters, depending on the open interval. Before moving to geothermal, I will present real cases in gas wells and oil wells. So you have the SP reference on the top here. So this was gas well with low permeability sandstone with high clay content. It was offshore. The treatment volume for each well was 40 cubic meter, and 16 wells were treated since 2013. And these are wells that were producing sand, and obviously the gas production could not be increased because of this sand production. So typically, when a treatment is performed, there is a soaking time of 12 hours, and the day after, the well can produce again, and the sand production is stopped right away. In this specific case, they could multiply by 2.5 the gas production after the treatment. Just few words about the oil wells. So this is, again, you have the references here if you need to see the publication. In this case, the permeability range from 140 to 300 millidarcy. The salinity of the water was 18,000 ppm. Temperature of the reservoir, 81 Celsius. The volume for the treatment is higher than for the previous gas wells, 150 cubes. And it was a gas lift, so you have a choke, and before the treatment, it was producing 1.5% of sand in the fluids. And right after the treatment, you see that it decreased to 0. It was the first one, and they could increase the flow rate afterwards because the sand was stopped. Since then, more wells were treated, and you have the number here. So the volume ranges from 115 cubes to 200 cubes. Those wells, some of the wells were producing water with oil and gas. The sand production was 2 to 3% of the fluids. And after the treatment, again, it decreased to 0. And one of the interesting points is that these wells were monitored for more than 4 months with no new production of sand. So from what we know from the oil and gas industry, the sand control using polymer is a proven technology. It can last 1 to 4 years without any sand production, but it can be repeated with the same efficiency. It can be deployed in large open intervals. I'm talking about horizontal wells. It's usually injected bullheaded. It can sustain salinity up to 300,000 TDS. The limitation in temperature today is 120 Celsius. That may be a concern for geothermal application, obviously. It was successful in underground gas storage wells and gas well, as well as in oil producer and in water injectors. So now let's move to the topic of today, which is what about applying this technology in the geothermal application. So the initial problem in geothermal is roughly the same than in oil and gas. It's you can lose injectivity or productivity in depth geothermal operation formation because of fine accumulation, either in the production or in the injection well. That generate loss of productivity. And today, the current solution is regular cleaning. So you need to handle backflow and water. Or you can also limit the flow rate, but you lose calories when you do that. So obviously, when you do that, you don't have any complete restoration of the well. You still, again, the sand accumulation can occur after the cleaning, and it can be in a matter of weeks or even days sometimes. And it's costly in terms of time, production, and logistic. So we had a sponsored project. So the ADEME, which is the Energy and Environmental Agency in France, sponsored the project. It was a 2 years project with 3 partners, Storengy, BRGM, and Poweltech. So just for the numbers, in France in 2022, 2.1 terawatt hour of geothermal energy was produced, and 2 terawatt were dedicated to it. Basically, the Paris Basin, this is deep geothermal in Dogger, so it's carbonates, and you don't have this kind of problems of sand migration, obviously, in these cases. But in France, we have many doublets, geothermal doublets in the Albian and Neocomian, which are sandstone formation in the Paris Basin, and these are the target for this specific project. The objectives of the project is to transfer the technology already successful in oil and gas to the geothermal application. And the goal is to stop or limit the fine production by coating rock surface using a polymer. But the challenges in geothermal industry is the flow rates. When you compare flow rates of oil industry, it's between 100 cubic meter to 1,000 cubic meter per day. And in geothermal, you are dealing with 250 cubic meter per hour. So it's a huge change, and we don't have any idea if the polymer can sustain such high rates around the wells. So obviously, what we need to assess in this project is the efficiency of the treatment to stop fine migration for how long, with this taking into consideration these flow rates, and to check the impact on well productivity and injectivity, obviously, because you don't want to lose neither injectivity and productivity. So the first step was to select a polymer and to do laboratory performance test. So as I said earlier, the target for this project is the Albian sand. So we need to collect sand in France for this specific project. And for the selection of product, what is performed is a quick flocculation test. So basically here you have a volumetric cylinder with some sand from the aquifer. You mix the sand with water, and then you start a timer, and you check the settle time to pass the 2 marks here you have in gray. But you see that when you don't have any polymer, in 60 seconds, you still have not settled the sand because you have a lot of sand in suspension. When you add the polymer to the water before mixing, and you start the timer, you can see that in 15 seconds, all the sand is settled and you have clear water on the top. When you have this result, it means that the polymer has very good sticky properties to the sun, and you can select this type of polymer for the specific sun. So this is what we did at the time for further core flood testing with the sun. So the laboratory performed tests consist in performing core flooding experiment using sand pack. So here you have the picture of the sand pack where we have packed the sand from the aquifer. But the challenges, there were different challenges. The first one being we have to handle very high flow rates. So we will consume a lot of water for the flow rates applied in geothermal application. And the second challenge was to assess fine migration within the sand pack. And for this purpose, we put at the outlet of the core a grid with 90 micron mesh pores so that the fine below 90 micron could migrate at the outlet of the core and we could collect them. A few words about the sand pack. So it's 8 centimeter length, 1.5 inch diameters. The pore volume is 37 milliliters and permeability range from 1.5 to 2.5 darcies. We did more than one core and this is the range we had. All the measurements for permeability were performed using 2% KCl brine to avoid the swelling of the clays, obviously. Then the brine of the reservoir was injected. It's a very soft brine, 0.6 gram per liter. And then we could see the sand production. We use an absorption curve to determine the concentration of the fine we collected. And you have the curve here with a wavelength of 600 nanometer. So this is the result of the core flood. You can see that we increased the flow rates from 50 milliliter per hour to 3,000 milliliter per hour, which is huge. And you can see the type of the fine we collected at the outlet in the small tubes. You see the color here. What was observed on the curve here, it's the sand concentration in gram per liter. You can see at 50 milliliter per hour, you have an increase of sand production and it stopped, of fine production, sorry, and it stopped. Then each time we increase the flow rate, you can see a bump of fine production and a decrease. For every flow rate, we have this result. So we could assess the fine production for the experiment, and it increases with the flow rate. In the same time, we monitor the permeability to water of the core. So it started from 1,200 millidarcy, and you can see that as soon as you inject soft water, and because you have sand migration, you have a drop of the permeability. So because of the sand migration, it generates a drop of relative permeability. But when we increased again the flow rate, you could see that the permeability increased again. This may be explained because you lose a lot of particles when you increase the flow rate, so that makes sense that the permeability increase again by the fact that you lose the material in the sand pack. So we have seen that we have managed to perform the test to assess the migration of sand in our sand pack. Now, what when we inject the polymer before performing the test? So in this case, we use the sand pack again, but before performing the increase of flow rate with the soft water, we inject a polymer solution in 2% KCl. Then we inject the soft water, and then we monitor the relative permeability and the fine production as we did before. So first of all, when we inject the polymer, we could determine the adsorption of the polymer. It was 180 microgram per gram of rock, and we had a permeability reduction below 1.5. But when we inject again, and I don't have curve because the curve is so flat, there's no fine production, whatever the flow rates in the effluent, once the polymer is in place. And we never detected polymer neither in the effluent. We went up to 8 liters per hour, which correspond to geothermal velocities. We can see that in the next slide. So typically, this is the speed in centimeter per second. And when we apply it, depending on the height of the open interval, you can see that the worst case is 0.7 centimeter per second. And the highest speed we evaluated is the one here is 0.63 centimeter per second. On the horizontal axis, this is this distance from the well. So anyway, as soon as you reach 20 centimeters, it drastically decreases the speed. For the conclusion for this study, we have a very good polymer that have very good affinity with the Albion sand. We managed to perform the destabilization of sandpack by the injection of low salinity brine. We could have fine production of fine particle, and this production increased with flow rate. As soon as we had the polymer, it stabilizes the sandpacks there. And when we again inject the low salinity brine, there was no fine in the effluents. The polymer was not detected in effluents, meaning that it really sticks to the sand particle. There is a low impact on water permeability, and we went up, as I said, to 8 liters per hour, which is 0.62 centimeters per second. So it can withstand geothermal velocities. If we compare from an economical point of view, doing regular cleanings from time to the polymer technology, when you do regular cleanings, you do backwashing over 4 years. So the comparison is for 4 years. You have intervention every 2 months, and that require 1 day each time. And that generates a loss of productivity and injectivity over time. Over 4 years, it's a loss of 10,080 megawatt hour, sorry. And you have to manage 6,000 cubic of backwash water. When you use the polymer technology, it's an intervention that lasts a maximum 3 days, so that to inject the treatment, you don't have to manage water, backwash water. Normally, you should have 4 years without any intervention, and you don't have any loss related to the injectivity. In terms of cost, you divide by 5 the cost when you use the polymer technology. You save energy, obviously, and water management. Just a scheme to explain how the polymer is injected. Typically, a polymer is either powder or liquid. We use 2% KCl brine to inject it, so we need storage tank to inject 2% KCl brine to dissolve the polymer. You need a flip-flop mixing tank system. While you are preparing a solution polymer, you inject the other solution, and so on. So it's a batch by batch injection. And this is the way it is applied. So this is the last slide of the talk. So for the conclusion, we have demonstrated by the laboratory that the polymer treatment is efficient for the geothermal application because it stopped the sand production even at high velocities. there is an irreversible adsorption of polymer of the rock because we never detected polymer in the backflow. The salinity for the application can be above 150 grams per liter. And obviously, the maximum temperature today for those polymers is 120 Celsius. I was talking about Albion application, which is 30 Celsius. But we have also the trias that is 80 that could be manageable. I'm not aware of others, but today 120 is the maximum range we can apply for this technology. So thank you for your attention, and I'm ready for the question if there are any.
Hear me?
Yes.
Perfect. I don't see any questions coming from the audience in the chat box, but I will ask you a couple. I found this very interesting. And Kevin actually asked the question that I was about to ask. Is asking, do you have any plans to increase the range at which the polymer could work in terms of temperature? Here is showing 120 C. Do you have any plans to try to go higher in terms of application?
So these polymers are organic molecules, and like organic molecules, they have a limitation. The thing is, you may have a good result right away, but it may last 5 days because you will lose the polymer will experience degradation. Sorry.
Mhm.
So today our plan is more to assess on the field that it works for geothermal application before proposing something for higher temperatures. Because
Gotcha.
today it has not been applied yet in a geothermal well.
I understand. So basically, the plan is to try to run it at, these temperatures below 120,
Mhm.
um,
To assess that
solidify it.
it works in real life, really.
Mhm. Gotcha. And then move higher.
We, we,
I,
we, we have planned we have planned for higher temperature, but to be honest, we will never have this technology with this specific family of polymer for above 150 C.
gotcha. But that still covers a very big part of conventional
Mhm.
doublets across many geothermal places. So 150 C is pretty good, right? I mean, you're still in the range of district heating, probably some power production. So you could see this application maybe become more. There is a question from Gary. Says, what is the mechanism for the polymer to stabilize the fines? It is not a glue, but some sort of filtration of the float space.
No,
Or does it
it's
increase the cohesion of the fines?
it's typical ionic adsorption. It's not a chemical reaction. It's either van der Waals force or ionic force. So we have made some charge on the rock and the opposite charge on the polymer. That's the way we may have this effect. But it stick, but there's no chemical reaction.
Gotcha. Does it work? So Hector says, does it work to reduce sand production after fracturing operations? So basically, I suppose backflow of sand. I think that's what he's talking about.
Yes, yes. So we had some application for propant backwash in fracking. It may work, but we have a very only maybe one well that was tried this way, and we don't have really feedback. So I'm curious about that. I know it may work, but we don't have
Yeah,
applied this a lot.
because I mean, generally in these kind of applications, the industry applies some resin coated propant, the idea of
Mhm.
trying to stop
Yes,
the backflow.
yes.
So,
Mm.
I guess, what about unconsolidated sands?
Say it again, sorry.
What about the sand production in some unconsolidated sands, reservoirs?
So yeah, okay, when it's really unconsolidated, this technology will not be enough. I was talking about fine production, which are 2, 3, up to 5%. But if you have more than that, it's really unconsolidated. you will need something stronger like a gel or resins or things like that.
Gotcha.
It's not the purpose.
Not for that magnitude. Okay.
Yeah.
Gary asked a follow-up question. It says, so it is the capillary force to keep the polymer in the pore space.
No, it's not the capillary force. It's just because if you remember well, the pictures I showed about the flocculation,
Mhm.
it really stick to the sun on the surface of the rocks because of ionic interaction between the rock and the polymer.
Gotcha. I do have a question. I was wondering, you showed a case study in the oil and gas, and there was a graph of, you know, uh, let's say enhanced production, quotes, quotes. What is the time that it sustains that kind of improvement? You know what I mean? Like, how often would you have to run these treatments?
So there are many parameters for this. It obviously depends on the history of the wells and the flow rates of the well.
Mm-hmm.
Basically, 2 years is a good average. So meaning that during 2 years you don't have any sound production, and you can see sound production after 2 years, but you can do again this treatment with the same efficiency at the time.
Gotcha.
It
And
also
the
depend. It also depends on the temperature um, and the tolerance of the polymer to the temperature.
gotcha. I'm getting a couple more questions from Ioana Popescu. How is shear degradation or possible polymer damage
It's
followed
a
up or typically tested? Is it a concern?
it's a very good question. Since during the injection we have limited flow rates, so you don't shear the polymer when you inject it, especially in large interval. So the shear is too low to have any degradation. Once the polymer is coated on the sun surface, as you could see during the performance test, there's no fine production. So it means that the polymer is not affected at the time it is once it is placed in the reservoir.
Gotcha. There's a follow-up from Kevin. It says, it would be interesting to have a downhole NMR log and see how the pore size distribution evolves before and after the polymer application. Do you maybe have any data on that? It's expensive to do that.
Well, if Gary, you are ready to do that, I am ready to go with you. But to be honest, today we are looking for um, companies who are ready to evaluate this technology in real life. So
Mhm.
we are open to this.
Interesting. Okay. I think that was the last question from the group. I guess one follow-up would be, with this kind of applications and basically what it can mean for, okay, never mind. How much polymer do you have to pump? I think you had mentioned some volumes here. That's what Gary was asking. What are typical
It's a good
volumes?
question. It's a good question. It depends if you treat an injection well or a production well. No, usually the volumes are lower for production wells than for injection well. To give you a range of uh, of volumes for geothermal application, it would range between 100 cubic meter to 800 cubic meter. It really depends on the flow rates and the open interval. If your open interval is really large, it may increase the volume.
So you are doing a conversion of what the flow area is between the injector and producer, and then using that in terms to infer the volumes, right?
Yes, actually, you don't want to inject this only for 10 centimeter around the wellbore. You need to invade between 50, 1 meter, and if you can, even higher distance, like 2 meters or 3 meters.
Gotcha.
So when you have a large open interval, obviously it increases drastically the volume.
Yeah, makes sense, and that affects the economics too. So,
Sure, sure.
there's another question. Well, it says, oh, it's a comment about the planning of the meeting. Yeah, I understand. It's about putting the time zone. I understand, Gary. But in this case, it's people that join these webinars come from all over the world and all over different time zones. So we try to stick it closer to where the speaker is. But your point is well taken. Thank you. Yeah, so Nicola, at this time, I don't see any more questions in the chat box. I would like to thank you for your time today. What we will do is we'll take this recording and upload it on our channel. I will
Mm-hmm.
also send it out to all the registered participants and share the link with you as well.
Mm-hmm.
Unless you have any, do you have any other comments?
From my side, no.
Okay, perfect. Well, thank you so much. Thank you to the audience, and stay tuned for our next talk in June.
Thank you.
Thank you.
Thank you, everybody. Bye.